What if the universe's greatest mysteries are not hidden in silence, but written all around us in ancient light? Bending spacetime, invisible black holes, wandering interstellar visitors, and distant worlds that may or may not be alive. Welcome to Calm Space Science, where we take a slow, peaceful journey through the deepest questions science can ask: how the universe began, why time moves forward, how black holes reveal themselves without shining, and what strange planets beyond our solar system may teach us about life. Before we begin, thank you for spending your time here and sharing this quiet moment of curiosity with us. If this kind of calm space science helps you relax, learn, or drift gently towards sleep, please like the video, subscribe to the channel, and share it with someone who loves the mysteries of the cosmos. And before the journey starts, what time is it where you are watching or listening from? And where in the world are you? Leave a comment below. Now, let's begin our calm journey through the universe's greatest mysteries. The oldest light in the universe does not arrive from stars. It comes from a time before stars had formed, before galaxies had gathered, before planets, oceans, minerals, or living cells had any place to exist. It is not bright in the ordinary sense. It is thin, cold, and stretched almost beyond recognition. Yet it fills the sky from every direction with a quiet regularity that makes it one of the deepest records science has ever found. This light is called the cosmic microwave background, and its existence gives the early universe something like a memory. It does not show the first instant itself. No telescope can yet look all the way back to that boundary, but it carries the imprint of a younger cosmos, a universe that was once hot enough, dense enough, and simple enough that matter and light were still bound together in a glowing sea. The Big Bang is often spoken of as an explosion, but that image is too small and too local. It was not matter bursting into empty space from a central point. It was the beginning of expansion everywhere. The unfolding of space itself, from a state where the observable universe was compressed into conditions so extreme that ordinary intuition no longer has much power. Every distant galaxy, every dark region between clusters, every quiet patch of interstellar dust belongs to a history that can be traced backward toward that early heat. The evidence begins with motion. When astronomers measure light from remote galaxies, that light is usually shifted toward longer, redder wavelengths. The effect means that, on average, distant galaxies are moving away, not because they are flying through a fixed stage, but because the space between galaxies is growing. Run that expansion backward in thought, and the separations shrink. Galaxies draw closer. The cosmic web contracts. Matter becomes more crowded. Radiation becomes more energetic. The universe becomes hotter. This does not prove that everything came from a mathematical point of infinite density. And careful physics does not require pretending that such a singularity is already understood. What it does show is that the observable universe had an earlier state unlike the present one. Smaller in scale, hotter in temperature, and denser in matter and radiation. That is the secure foundation beneath the mystery. The phrase Big Bang names this hot early expansion, not a settled answer to why there was something rather than nothing, and not a complete description of the first moment. In that distinction, the subject becomes more interesting rather than less. A beginning can be strongly supported by evidence while its deepest cause remains unknown. The young universe, in its earliest observable form, was not empty darkness. It was a plasma, a state in which matter was so hot that electrons could not settle into stable atoms. Light could not travel freely through it. Photons, the particles of light, were constantly scattered by charged particles, absorbed and redirected in a dense, glowing fog. Space existed. Time passed, and expansion continued. But the universe was opaque. It had not yet become transparent to its own light. As expansion stretched the cosmos, the temperature fell. This cooling was not a local process, like a fire burning down in one place. It happened everywhere, as space grew and radiation lost energy. After hundreds of thousands of years, the temperature dropped enough for electrons to join atomic nuclei. Hydrogen and helium atoms formed. The fog lifted. Photons were suddenly able to move across space without being constantly scattered. The light released at that transition has been traveling ever since. Over immense cosmic time, the expansion of space has stretched it from visible and infrared wavelengths into microwaves. What began as the glow of a hot young universe now appears as a faint, cold signal. A background radiation arriving from all directions. The discovery of that signal did not come from a dramatic search for the origin of everything. It came through an unwanted noise. In the middle of the 20th century, Arno Penzias and Robert Wilson were working with a sensitive horn antenna, trying to understand persistent radio interference. The signal did not behave like local equipment trouble. It did not seem tied to a nearby source. It remained no matter where the antenna pointed. Even practical explanations failed. The noise was steady, directionless, and strangely universal. At the same time, other physicists had been considering whether a hot early universe should have left behind a cooled remnant of radiation. The unwanted noise turned out to be the clue. It was not interference in the ordinary sense. It was the afterglow of the early universe, reduced by expansion to a cold microwave whisper. The importance of the cosmic microwave background lies not only in its existence, but in its shape. It is almost perfectly uniform, as though the early universe had reached a remarkable smoothness before structure began to grow. But almost is the essential word. Embedded in the background are tiny differences in temperature, minute variations that reveal where the young cosmos was slightly denser or slightly thinner. These differences are small, yet they matter profoundly. Gravity requires unevenness, without some regions holding a little more matter and energy than others. There would be no preferred places for gas to gather. No first stars, no galaxies, no clusters, and no later worlds built from heavier elements. The early universe had to be smooth enough to produce the broad order seen today, but irregular enough to permit structure. The cosmic microwave background records that delicate balance. It is both calm and seated, both uniform and quietly uneven. From those faint variations, the future architecture of the cosmos begins to become possible. A slightly denser region bends spacetime a little more than its surroundings. Matter falls toward it. The region grows denser still. Over time, this small advantage strengthens. The first great structures are not imposed from outside. They emerge from gravity, acting patiently on tiny initial differences. What looks, in the modern universe, like a majestic web of galaxies and dark voids, has roots in those small temperature patterns across the ancient light. In this way, the cosmic microwave background is not simply a relic. It is a map of potential. It shows the universe before stars, but it also hints at where stars will someday form. It belongs to a time when there were no familiar objects. Yet, it already contains the statistical beginnings of everything familiar. There is another reason the early universe matters. Its temperature did more than make the cosmos glow. It allowed the first simple nuclei to form. In the first minutes, when the universe was still extraordinarily hot. Protons and neutrons combined in limited ways, producing mostly hydrogen and helium, with traces of other light elements. This process, known as Big Bang nucleosynthesis, left behind a chemical pattern that can still be tested. The amount of helium in the universe is not random. It agrees with the idea that the early cosmos passed through a brief, hot nuclear phase before cooling too much for that fusion to continue. Later stars would make heavier elements, but they did not create the original cosmic abundance of hydrogen and helium. That first simplicity is another fossil, not of light this time, but of matter itself. The universe begins, as far as observation can reach, not with complexity, but with a few basic ingredients under extreme conditions. Complexity comes later, through gravity, time, stellar fire, and the repeated recycling of matter. Yet the greatest caution remains at the beginning. Physics can describe the universe back to extraordinarily early conditions, but the closer the calculation moves toward the first boundary, the more the known theories strain. General relativity explains gravity as the curvature of spacetime, and quantum physics describes the behavior of matter and energy at very small scales. The first universe seems to require both at once. At such densities and energies, neither theory alone is enough. The singularity often associated with the Big Bang may therefore be less a proven physical object than a sign that current equations have been pushed beyond their safe range. This does not weaken the evidence for a hot early universe. It marks the place where explanation becomes incomplete. The observable trail is strong expanding space. The background glow, the abundance of light elements, and the growth of structure from small fluctuations. The unanswered question is what lies beneath that trail. Was there a true beginning of time? Or did some earlier condition give rise to expansion? Did spacetime itself emerge from something deeper? Or is that question shaped by language more than by physics? Science has not settled this. It has only drawn the boundary with increasing precision. The calm power of the cosmic microwave background comes from that combination of certainty and restraint. It does not reveal everything. It does not explain why the laws exist, why the universe has the properties it has, or what, if anything, preceded the earliest describable phase. But it does show that the present cosmos is not eternal in its present form. It has cooled. It has expanded. It has changed from a hot, opaque state into a transparent universe where stars can shine and observers can look back. The night sky, which seems so dark, is therefore layered with an ancient glow that ordinary eyes cannot see. Behind the stars lies the remnant light of a time before stars. Behind the galaxies lies the pattern of small differences that allowed galaxies to begin. Behind the calm appearance of empty space lies a record of heat, expansion, and transition. The first mystery is not simply that the universe began. It is that the beginning left evidence, and that this evidence remains readable after so much time, stretched thin across the sky, waiting as a cold and patient signal from the young cosmos. Inflation begins as a quiet problem hidden inside an otherwise powerful story. The early universe, revealed by its ancient afterglow, is even in too many directions. Regions of the sky that should never have had time to exchange heat appear to carry almost the same temperature. The cosmic microwave background is not perfectly smooth, because its tiny variations are the seeds of later structure. But its broad uniformity is striking. One distant patch of that radiation looks almost like another, even though the space between them has expanded so much that ordinary communication between those regions seems impossible. Without some additional event, the young universe appears too coordinated for its own age. Inflation was proposed to solve that tension. It describes a brief phase when space itself expanded with extraordinary speed, stretching a tiny region into a cosmic domain large enough to contain everything now visible. Nothing raced through space faster than light. The rule against faster-than-light motion still applies to objects, signals, and information moving locally. Inflation uses a different door. It is space that grows. And as space grows, distances between regions can increase faster than any object could travel across them. This distinction matters because it removes the apparent paradox without making the event any less strange. The universe does not outrun light like a particle breaking a speed limit. The stage on which particles exist swells beneath them. Carrying separated places apart before ordinary motion has much chance to matter. For an almost unimaginably brief interval, expansion becomes the dominant fact. A region far smaller than an atom can become vastly larger, not by pushing outward into empty surroundings, but by multiplying the scale of space within itself. The image is difficult because daily experience offers no true comparison. A balloon surface gives only a partial hint, because the surface stretches while points on it move farther apart. Yet even that image can mislead. Since the universe is not known to expand from a center into an outside room, expansion happens everywhere at once. Every place participates. Every distance can lengthen. The question is not where the center is, but how the scale of all separations changes with time. Inflation takes this idea and intensifies it beyond ordinary expansion. It says that the young cosmos passed through a runaway enlargement, a nearly instantaneous smoothing and stretching that changed the future conditions of everything inside it. The smoothness matters first. If a small region was once compact enough for temperature and energy to settle into near uniformity, then inflation could stretch that already even region across the observable universe. What appears puzzling across the modern sky may therefore be a memory of a time when all those regions were once close together. The universe looks coordinated because, before inflation enlarged it, the relevant parts may have shared a common physical history, but inflation does not erase all variation. It cannot, and the cosmos would be barren if it did. Quantum physics, which governs the smallest scales, never allows perfect stillness. Even in a field that seems uniform, tiny fluctuations remain. Inflation stretches those microscopic irregularities to enormous size. What begins as a small tremor in energy becomes a large-scale difference in density. The process turns quantum uncertainty into cosmic architecture. This is one of the most remarkable parts of the idea. The later positions of galaxies may trace back to fluctuations so small that they belonged originally to the hidden grain of quantum fields. Inflation, therefore, acts both as a smoothing force and as a magnifier. It explains why the universe is broadly uniform while preserving the little unevenness gravity needs in order to build. After inflation slows or ends, the universe does not simply remain empty and cold. The energy associated with the inflationary state must be transferred into particles and radiation, reheating the cosmos and setting the conditions for the hot early universe already described by the Big Bang model. This handoff is one of the places where certainty thins. The broad outline is useful, but the detailed mechanism depends on physics not yet fully confirmed. Something must end the accelerated expansion. Something must populate the universe with the matter and radiation that later combine, and form the background light. Different models propose different forms of the field responsible for inflation, often called the inflaton. though no such field has been directly identified. The name gives the unknown a handle, not a final explanation. The strength of inflation is that it connects several otherwise difficult facts. The weakness is that its deepest machinery remains partly theoretical. Good cosmology has to hold both truths at once. The evidence for a hot expanding universe is strong. The evidence for a very early inflationary phase is persuasive in its ability to explain patterns, but the exact physical cause remains unsettled. Still, the idea reshapes the meaning of expansion itself. Expansion is not merely a slow spreading of galaxies through pre-existing space. It is the behavior of space as a dynamic part of the universe. In the present era, distant galaxies recede because the fabric between galaxy clusters grows. On smaller scales, gravity holds systems together. Earth does not expand away from the sun. The solar system does not swell with the cosmic scale. Galaxies themselves remain bound. Expansion becomes important across the immense distances where no stronger local binding resists it. At those scales, the cosmos is not a static container. It changes its own measure. Light traveling through it is stretched. Ancient wavelengths lengthen. A glow once hot enough to fill the sky with visible brightness cools into microwaves. Distance and time become tied to the expansion history, so that looking far away also means looking backward, through stages of the universe when the scale of space was smaller. This connection gives observational astronomy its deep temporal reach. A telescope does not merely collect light from elsewhere. It gathers evidence from earlier conditions, and the expansion of space records itself inside that light. The slight redshifts of nearby galaxies, the larger redshifts of remote ones, and the cold background radiation all belong to the same unfolding pattern. The farther the evidence is pushed back, the more the universe appears not as a collection of objects placed in a fixed arena, but as a history of changing scale. Inflation adds an even earlier chapter to that history. Before atoms, before free-traveling light, before stars, and before the structures that later make the sky recognizable. It suggests that the largest observable features may have been shaped by an event so brief that ordinary time language feels too heavy for it. Yet its consequences are not brief. They remain written across the cosmic microwave background, across the distribution of galaxies, and across the overall flatness of space on the largest scales. Flatness here does not mean empty or featureless. It means that, when measured on cosmic distances, the geometry of space appears very close to balanced, neither sharply closed like the surface of a sphere, nor widely open in a strongly curved way. Inflation naturally drives space toward that kind of large-scale flatness, stretching curvature until it becomes difficult to detect. A small curved patch can look almost flat if enlarged enough. In this sense, inflation may have taken an earlier geometry and spread it so widely that the observable part now seems nearly level. There are still missing pieces. Cosmologists look for subtle signatures that could strengthen or weaken the case, including possible patterns in the polarization of the cosmic microwave background. Such patterns might carry traces of gravitational waves from the inflationary era, ripples in spacetime produced when the universe was young beyond direct sight. The search is delicate because the signal, if it exists, is faint and easily confused with foreground effects from dust and magnetic fields in the Milky Way. The difficulty is not a failure of the idea. It is a reminder of how narrow the evidence channel becomes near the beginning. The universe may have recorded inflation, but the record is written in pale marks across ancient radiation, partly obscured by everything between then and now. What remains powerful is the shift in perspective. The cosmos is not only expanding now, Its present structure may depend on an early episode when expansion did the work that no ordinary process could do. It smoothed the sky without making it sterile. It stretched tiny fluctuations into future gathering places. It allowed a hot beginning to become a universe with patterns rather than a featureless glow. The mystery, therefore, moves from whether space expands to how deeply expansion shaped reality before matter had settled into familiar forms. The first light showed that the universe remembers its youth. Inflation suggests that even before that light was released, space had already performed its most decisive transformation, enlarging the smallest uncertainties until they became the quiet framework on which galaxies could later gather. Curved reality does not announce itself in daily life. A stone falls. A moon keeps circling. Oceans rise under lunar pull. And the motions look familiar enough to seem almost simple. Gravity appears to be a force acting across distance, a hidden hand that draws matter toward matter. But general relativity changes the meaning of that pull. In Einstein's description, gravity is not merely something objects exert on one another through empty space. It is the response of space and time to the presence of mass and energy. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. The statement is compact, but its consequences reach from the fall of an apple to the paths of galaxies and the final collapse of massive stars. The universe is not built inside a rigid container. Its container bends, its distances stretch. Its clocks do not all keep time in the same way. What appears as a force can be understood as motion along the natural paths of a curved geometry. A planet orbiting a star is not being dragged around an invisible circle in the old sense. It is following a path through space-time shaped by the star's mass. A path that looks curved because the underlying structure is curved. This is difficult because the curvature is not usually visible. There is no glowing grid around the sun, no visible depression around Earth, no bright track showing the way the moon moves through a warped environment. Yet the effects are measurable with great precision. The orbit of Mercury, the bending of starlight near the sun, the slowing of clocks in stronger gravity, and the timing corrections required for navigation satellites all point toward the same quiet fact. Spacetime is active. It is not background scenery. It participates in the behavior of the cosmos. The first great test came when starlight passed near the sun and arrived at Earth from a slightly shifted position. The light had not been pulled like a pebble in the ordinary way, because light has no rest mass. Its path changed because the geometry it traveled through was curved. During a solar eclipse, when the sun's glare was hidden, the positions of stars near the solar edge could be measured. Their apparent displacement supported the idea that mass bends the route taken by light itself. That result was not just a confirmation of one prediction. It changed the emotional scale of gravity. The sun was no longer simply a massive body attracting planets. It became a sculptor of geometry, reshaping the lines by which even radiation moves. From there, the idea widens. If a single star can bend light, then a galaxy or cluster of galaxies can bend it more. Gravitational lensing turns distant galaxies into arcs, rings, or duplicated images. Not because the galaxies themselves have strange shapes, but because their light has crossed curved spacetime on the way to observation, the universe becomes, in part, an optical system made by gravity. It can magnify what lies behind it, distort what passes through it, and reveal mass that does not shine. This matters especially for dark matter, whose presence is inferred not from light but from gravity. Lensing maps show where invisible mass must be, because the path of background light carries the imprint of the foreground curvature. In this way, Curved spacetime becomes a tool for seeing what cannot otherwise be seen. The geometry is not decorative. It is evidence. It records mass, visible and invisible, across distances too large for ordinary intuition. Gravity also changes time. This is one of the most unsettling and most carefully confirmed parts of the theory. A clock deeper in a gravitational field runs more slowly than a clock farther away, near Earth. The difference is small, but it is real. Atomic clocks at different elevations reveal it, and satellites must account for it because their clocks do not match clocks on the ground perfectly. The effect is not a flaw in the clocks. It is a feature of time itself. Time is woven into the same structure as space, and that structure is affected by mass. A second is not absolutely identical everywhere in the universe. It depends on motion and gravity. Near a compact object, where curvature grows stronger, the difference becomes more dramatic. Near the edge of a black hole, time relative to distant observers can slow almost beyond comparison. The closer the path moves toward the event horizon, the stronger the distortion becomes. This does not mean that time feels broken locally for matter falling inward. Local physics remains locally consistent, but from far away, the falling object appears increasingly delayed and dimmed. Its signals stretched and weakened as spacetime imposes its geometry on both motion and light. The event horizon is therefore not a material surface. It is a boundary in spacetime, a place where the future directions available to light and matter all lead inward. Such a boundary is one of the most extreme consequences of curved reality. It shows what happens when mass is concentrated so tightly that curvature closes off escape. Yet even before black holes appear, general relativity gives the universe a new kind of motion. Spacetime itself can ripple. When massive bodies accelerate, especially when dense objects orbit each other closely, they can produce gravitational waves, faint disturbances traveling outward at the speed of light. These waves are not sounds moving through air, and not electromagnetic radiation. They are passing changes in distance, tiny rhythmic stretches and squeezes in the geometry of space. For a long time, they remained a prediction. Elegant but difficult to catch. The waves from distant collisions are extraordinarily weak by the time they reach Earth. Detecting them requires measuring changes far smaller than the width of an atom across instruments kilometers long. Yet such measurements have been made. When two black holes merge, or when neutron stars spiral together, the final moments send ripples across spacetime. By the time those ripples pass through Earth, they are faint, but their pattern still carries information about the masses, spins, and distance of the source. This has opened a new form of astronomy. The universe is no longer studied only by collecting light. It can also be studied by sensing the motion of spacetime itself. That change brings the invisible closer without making it ordinary. A black hole merger may leave no flash visible to a telescope, yet its gravitational wave signal can trace the collision's final orbit. Neutron star mergers can produce both waves and light, linking geometry to radiation and matter in one event. Each detection strengthens the idea that spacetime behaves not as a passive stage, but as a physical participant, capable of carrying energy and information. The same framework also shapes the largest question of all the expansion of the universe. General relativity allows spacetime to expand, curve, and evolve according to its contents. It provides the language in which modern cosmology describes a universe whose scale changes with time. The same theory that explains the bending of light near the sun also helps describe the dynamics of cosmic expansion, the formation of structure, and the pull of galaxy clusters. This unity is part of its beauty. One set of ideas connects falling bodies, orbiting planets, gravitational lens, black holes, waves, and the changing scale of the cosmos. But that unity is not complete. At small scales, quantum physics rules matter and energy with a different language. At enormous densities, especially near the earliest universe or deep inside black holes, the two languages must somehow meet. General relativity treats spacetime as smooth. Quantum physics suggests that, at the smallest scales, smoothness may not survive. The tension is not a minor technical gap. It marks a frontier. If spacetime can curve, stretch, ripple, and form horizon, then the deeper question is what spacetime is made of, or whether it is made of anything at all. It may be fundamental, one of the basic facts from which all others begin, or it may emerge from a more hidden structure. As temperature emerges from the motion of particles, even though temperature itself is not a single particle, no confirmed theory has yet settled this. The known equations work with extraordinary power across a wide range of conditions, but they may not be the final description. That uncertainty does not make spacetime vague. It makes it more precise. Science has learned enough to know where the theory is reliable, and enough to recognize where it begins to ask for something deeper. The curved reality described by general relativity is therefore both a triumph and a threshold. It explains why gravity is not simply an invisible pull. It turns mass into geometry, motion into pathways, light into a tracer of curvature, and time into something shaped by where it passes. Yet it also points beyond itself, toward black holes, the beginning of expansion, and the unresolved meeting place between the cosmic and the quantum. The universe revealed by spacetime is not a collection of objects scattered through emptiness. It is a changing structure whose shape guides everything within it, while still concealing the deeper rules that give that structure its form. Time's direction is so familiar that it almost hides from thought. Ice melts, smoke spreads, a star burns through its fuel, a living body ages. Records form only after events have happened, and memory points backward rather than forward. Nothing in ordinary experience suggests that tomorrow and yesterday are interchangeable. Yet many of the basic laws used to describe matter do not seem to contain that same preference. In a simple collision between particles, the equations can often run forward or backward without breaking. A film of two billiard balls meeting and separating may look physically possible even if reversed. At the deepest mathematical level, much of microscopic physics does not loudly announce a preferred direction. The arrow appears when many particles are involved. When heat, disorder, probability, and information begin to matter. The question is not why individual atoms can move according to reversible rules. The question is why the universe made from them behaves as though it has a past behind it and an unwritten future ahead. The usual name for this direction is the arrow of time, and its most powerful link is entropy. Entropy is often described as disorder, though the word needs care. It is not merely messiness in a casual sense. It is a measure of how many microscopic arrangements can produce the same large-scale condition. A neatly stacked deck of cards has few arrangements that preserve its order. A shuffled deck has many. A warm cup of coffee cooling in a room has countless ways for its energy to spread into the surrounding air. The reverse event, in which scattered heat spontaneously gathers back into the cup and makes it hot again, is not forbidden by the motion of atoms in an absolute logical sense. It is simply so unlikely that, across ordinary life, and even across cosmic history, it does not appear. entropy rises because there are overwhelmingly more ways for energy and matter to be spread out than to be arranged in a narrow, ordered state. This statistical tendency becomes the steady current underneath irreversible experience. A broken glass does not rebuild itself because the fragments, air molecules, vibrations, and heat have moved into an enormous range of possible arrangements. The original glass represents only a tiny island in that ocean of possibilities. The same principle applies beyond rooms and small human scenes. It reaches into stars, planets, black holes, and the whole expansion of the cosmos. A star appears ordered because gravity gathers gas into a sphere. But the star also burns nuclear fuel and radiates energy into space. It creates local structure while increasing entropy overall. Life does something similar on a smaller scale. A cell maintains intricate internal order, but only by consuming energy and releasing waste heat into its surroundings. Order can grow in one place when a larger increase of entropy happens elsewhere. The arrow of time does not forbid islands of complexity. It sets the cost of their existence. Galaxies, ecosystems, weather patterns, and nervous systems all persist by moving energy through themselves. They are not exceptions to the second law of thermodynamics. They are shaped by it. The universe is able to build stars and planets not because entropy is absent, but because gravity opens pathways where matter can clump while radiation and heat spread outward. This makes the early universe deeply puzzling. It was hot, dense, and nearly uniform. And at first glance, that might sound like disorder. Everything was compressed into a state far simpler than the present cosmos, and temperatures were extreme. Yet in gravitational terms, that early smoothness represents a remarkably low entropy condition. Gravity changes the intuition. For gas in a box, a smooth distribution may be high entropy because the material is evenly spread. For a universe ruled by gravity, evenly spread matter is not the final disordered state. Given time, gravity pulls matter into denser regions, forming stars, galaxies, clusters, and eventually black holes. The early universe's smoothness therefore left enormous room for entropy to increase. It was not a finished chaos. It was a beginning with unrealized possibilities. Tiny density fluctuations existed, but the broad state was extraordinarily even. From that low entropy beginning, the arrow could point forward. Structures formed. Stars ignited. Heavier elements were made. Planets condensed. And radiation traveled into widening space. Each step added new forms of complexity while allowing the overall entropy to grow. The strange part is that the arrow of time may therefore be tied not only to physical laws, but to the boundary condition of the universe itself. The laws describe how systems evolve. The early state decides which direction that evolution seems to flow. If the universe had begun in a condition of maximum entropy, there would be no useful arrow, no long history of increasing disorder, and perhaps no room for stars, chemistry, or life. The presence of an arrow suggests that the beginning was special. The cosmic microwave background supports that picture by showing an early universe that was astonishingly uniform, with only slight variations. Those variations were enough for structure, but not enough to erase the overall smoothness. The universe began, as far as the evidence reaches, in a condition that made future change possible. Time's direction may be the long consequence of that fact. This also links time to memory. A memory is a physical record, a pattern in matter that points to an earlier event. Fossils, tree rings, cratered surfaces. photographs, and neural connections all exist because entropy has moved forward in a way that preserves traces of what came before. The past leaves records because it was involved in producing the present. The future has not left records because its detailed arrangements have not yet been selected from possibility. This is not merely a limitation of human awareness. It is a feature of physical processes. Records form through irreversible interactions. Light strikes a detector. Heat moves. Molecules rearrange. A surface is marked. Each record costs entropy. The reason the universe can contain evidence of its own history is the same reason broken glass does not reassemble. The flow that makes destruction ordinary also makes memory possible. The cosmic microwave background is a memory of the early universe because photons were released, stretched, cooled, and preserved along paths that lead into the present. Meteorites are memories of the young solar system because minerals locked in ancient conditions and survived. The arrow of time is therefore not only a philosophical problem, it is the reason evidence can exist. Without it, there would be no stable distinction between cause and trace. No layered past readable inside the present. Near the extremes, the problem grows sharper. Black holes carry entropy on a scale far beyond ordinary matter, and their horizons reveal a connection between gravity, information, and thermodynamics that remains unfinished. A black hole seems simple from the outside, described by mass, spin, and electric charge, but matter falling in may carry vast information. If black holes slowly emit radiation and eventually shrink, does the information vanish, or is it preserved in a form too subtle to read? The issue matters because time's direction is linked to information loss, irreversibility, and the difference between what can be known before and after a process. Black holes turn entropy from a property of hot gas or spreading heat into a feature of spacetime itself. A horizon has an associated entropy, as though the geometry of a boundary can store a count of hidden possibilities. This does not make the arrow of time disappear. It makes the arrow deeper. At the opposite end of cosmic history lies another limit. If expansion continues and stars eventually exhaust their fuel, the universe may move toward a thin, cold state in which useful energy gradients fade. New stars would no longer form. Existing stars would die. White dwarfs would cool. Black holes might dominate the long future before slowly radiating away across immense timescales. This possible fate is sometimes called heat death, not because everything is hot, but because energy would become too evenly spread to do work. The arrow of time would not stop in a dramatic instant. It would lose the conditions that make change rich. Complexity depends on differences, hot and cold, dense and thin, light and dark, ordered and disordered. As those differences fade, the universe would become quieter in the physical sense, less able to build new structures. The future, in this view, is not a final explosion, but a long thinning of possibility. The mystery of time's direction, therefore, reaches from the first smoothness to the last fading gradients. It begins with an early universe whose low entropy gave history room to unfold. It continues through every irreversible process, every star that burns, every planet that cools, every record that survives. It appears in the fact that evidence accumulates behind events and not ahead of them. It deepens near black holes, where entropy and information meet curved spacetime in ways still not fully understood. The arrow of time is not simply a clock ticking. It is the structure of change itself, a quiet asymmetry running through a universe whose basic laws do not always explain why one direction feels so natural, What remains unresolved is not whether time has a direction in experience. It plainly does. The harder question is why the cosmos began in the kind of state that allowed such a direction to exist at all, and why the passage from order into spreading possibility became the path on which all later mysteries had to travel. A massive star does not become a black hole because it grows dark. It becomes one because the pressure inside it can no longer hold matter apart. For most of its life, the star survives through balance. Gravity pulls inward with enormous patience, while nuclear fusion in the core pushes outward, releasing energy as lighter atoms are built into heavier ones. The light that escapes from the surface is only the outer sign of a deeper negotiation. Inside, every second of brightness is paid for by the slow conversion of fuel. A star like the Sun can keep that balance for billions of years. But the most massive stars live differently. Their brightness is a form of extravagance. They burn through fuel quickly, compressing their futures into a few million years, passing through stages of fusion that build heavier and heavier elements in the core. Hydrogen gives way to helium. Helium gives way to carbon, oxygen, silicon, and finally iron. That last step changes the meaning of the star's interior. Fusion up to iron can release energy. Fusion beyond iron costs energy. When the core becomes dominated by iron, the engine that once resisted gravity begins to fail. The star may still look immense from outside, but its center has become a place where support is running out. The collapse begins not as a visible catastrophe, but as a failure of pressure in the core. Gravity gains the argument. Matter falls inward at extraordinary speed. Atomic structure, once spacious enough to make the ordinary world seem solid, is crushed into a far more compact state. Electrons are forced into protons, forming neutrons and releasing a flood of neutrinos. The core shrinks violently. For a brief moment, it may stiffen as nuclear densities are reached, and the inward fall of outer layers meets the rebounding core and the escaping neutrinos. The result can be a supernova, a detonation so luminous that a single dying star may rival the light of its host galaxy. Yet the explosion is not the black hole itself. It is the visible upheaval surrounding the deeper question of what remains. The outer layers are thrown into space, carrying newly made elements into the surrounding darkness. Oxygen, silicon, sulfur, calcium, iron, and many other ingredients are scattered into future clouds, future stars, and future rocky worlds. The death of the star becomes part of cosmic chemistry, but at the center, where the collapse was most intense, the remnant must settle into one of only a few possible states. If the mass left behind is low enough, the core can become a neutron star, an object only a city's width across, where matter is packed so tightly that a small amount would weigh impossibly much by earthly standards. A neutron star is already an extreme answer to gravity. It is not ordinary matter compressed harder. It is matter in a state that has crossed nearly every familiar boundary. Light can still escape from its surface, and pressure from nuclear forces can still resist further collapse. But this resistance has a limit. If too much mass remains in too small a volume, no known pressure can hold the remnant up. The collapse continues beyond the neutron star state. At that point, the object does not merely become denser. It changes the structure of escape. Gravity curves spacetime so strongly that there is a boundary from which outward paths no longer lead outward. This boundary is the event horizon. It is not a shell, not a surface made of material, and not a place where matter necessarily strikes something solid. It is a one-way limit in the geometry of spacetime. Inside it, all possible future paths for light and matter tilt inward. The phrase, "nothing can escape," does not mean that light is too weak to fight gravity in a simple tug of war. Light always travels locally at light speed. The issue is that spacetime itself has been curved so deeply that the outward direction no longer reaches the outside universe. The black hole is born when collapse makes such a boundary unavoidable. That birth may be hidden inside the violence of the supernova, or it may occur through a quieter failure. When a very massive star collapses with little visible explosion and much of the material falls inward, the universe may produce black holes through more than one path, and the details depend on the original star's mass, rotation, composition, magnetic fields, and the amount of matter expelled before death. Massive stars shed material through winds. Some exchange mass with companions. Some spin rapidly enough that their cores are altered by rotation. Some die in environments where the chemical composition changes how much mass they lose before collapse. These differences matter because the final remnant is not determined only by how large the star once appeared. It depends on what gravity is left holding when the last stable support fails. A star can begin as a giant and leave a neutron star. Another can begin with still greater mass and leave a black hole. Between those outcomes lies a threshold that nature does not label cleanly for observation. The boundary must be inferred from remnants, explosion, missing stars, and the behavior of matter around compact objects. What makes black hole birth especially difficult is that the defining object is not the brightest part of the event. The supernova can be seen. The expanding debris can be mapped. The newly enriched gas can glow for centuries. But the black hole itself emits no light from within its horizon. Its arrival is known by what gravity does after the star is gone. In some cases, a companion star may reveal it, losing gas into an unseen compact object. In others, the collapse may leave a faint absence where a bright star once existed. There may be explosions that fail or fade unexpectedly, hinting that the core swallowed much of the energy that might otherwise have escaped. The birth of a black hole is therefore partly an event and partly a disappearance. It is a star reaching the end of the processes that made it shine, followed by a remnant whose most important feature is a boundary that cannot send news back out. This is why black holes can feel like monsters in popular language. Yet the scientific unease is subtler. They are not frightening because they roam through space, devouring everything nearby. Most black holes are small compared with the distances between stars, and matter must pass close enough to be captured. Their real force lies in what they reveal about the limits of theory. A black hole is a consequence of general relativity taken seriously under extreme conditions. Once enough mass is compacted within a small enough region, an event horizon follows from the equations. But what happens deeper inside is not settled. General relativity points toward a singularity, a place where density and curvature become infinite. But infinities in physics often signal that a theory has been pushed beyond the range where it can speak safely. The collapse that births the black hole is therefore anchored in well-tested gravity, while the innermost endpoint remains an open problem. The newborn black hole may have only a few times the mass of the Sun, yet its presence changes the surrounding region completely. Any remaining gas that falls toward it can form a disk, heating through friction, compression, and orbital shear until it shines in high-energy radiation. Magnetic fields can shape jets in some systems, sending matter outward from regions near the hole before it crosses the horizon. These displays can be brilliant, but they are not light from the black hole's interior. They are the last radiance of material still outside the boundary. Matter, surrendering energy as it spirals inward. This distinction gives black holes their peculiar observational character. The object is dark by definition, but its environment can be among the most luminous in the universe. A black hole is not seen directly in the ordinary sense. It is outlined by the behavior of matter, light, and space-time around it. In the life of a massive star, this is the final inversion. Brightness builds the elements, supports the core, and marks the star's presence across great distances. Then the source of brightness fails. Gravity wins the interior, and the remaining mass may become an object defined by the absence of escape. The transformation is not simply death. It is a transfer from stellar physics into extreme gravity. The star's outer material enriches space, while the core becomes a test of the deepest rules known. From the outside, the process can be followed through explosions, remnants, and missing light. From the inside, if that phrase still has meaning past the horizon, the known map runs out. The birth of a black hole closes the life of a star, but it opens a sharper kind of mystery, because the darkness left behind is not empty. It is curved spacetime, holding the memory of collapse in a form that can no longer shine. The invisible object is often found first by the matter that fails to stay invisible around it. Gas drawn from a companion star does not fall quietly into a black hole. It gathers angular momentum, spreads into a disk, and moves faster as it spirals inward, until compression, friction, and magnetic turbulence heat it to temperatures far beyond the surface of an ordinary star. The black hole itself contributes no light from inside the event horizon, but the material still outside that boundary can shine fiercely before crossing it. This is why some of the earliest strong candidates were not discovered as dark circles against the sky, but as intense sources of X-rays. High-energy radiation becomes a signpost for an object too compact to be seen directly. The evidence begins with consequence. Something massive and unseen is pulling gas into extreme motion. Something small enough to remain hidden is forcing that gas to release energy in a narrow, violent region. The task is then to decide what the unseen object can be. A normal star is too large. A white dwarf has limits. A neutron star can be dense and dark by ordinary standards, but it still has a surface and a maximum mass. If orbital measurements show that the unseen companion is heavier than a neutron star can plausibly be, and if the region producing radiation remains extraordinarily compact, the black hole interpretation becomes difficult to avoid. This is not seeing in the simple visual sense. It is measuring the shape of absence through the behavior of everything nearby. Binary systems are especially valuable because they turn gravity into a clock. When a visible star moves around an unseen companion, its spectrum shifts slightly as it approaches and recedes. Those shifts reveal the rhythm of the orbit. From the orbit, astronomers can infer the mass of the hidden object, though the calculation depends on the angle of the system and other details that must be handled with care. In the strongest cases, the hidden mass rises above the known limit for neutron stars. The companion is too heavy to be a white dwarf, too compact to be an ordinary star, and too dark to be anything familiar. Around some candidates, the pattern of X-rays flickers rapidly, implying that the emitting region is very small. Matter cannot vary that quickly if it is spread across a wide area. The faster the flicker, the smaller the region that can be responsible. These clues do not stand alone. They overlap. Mass, size, brightness, timing, and the absence of a visible surface begin to form one consistent picture. A black hole is not declared because the object looks mysterious. It is inferred because alternative explanations are squeezed away by measurements. Neutron stars remain important in this process because they are the closest imposters. They can pull gas from a companion, produce X-rays, rotate rapidly, and generate intense magnetic fields. Some reveal themselves through pulses, thermonuclear bursts, or radiation from a hard surface. A black hole should not show the same surface behavior, because matter crossing the horizon no longer strikes a material boundary that can flash back to the outside universe. The difference is subtle, and nature does not always make it easy. Accretion disks can change. Jets can appear and fade. Dust can obscure. Measurements can be uncertain. Yet the comparison with neutron stars makes the case sharper. The question is not simply whether an object is dense and dark. The question is whether it is dense and dark in a way that no surface, no stable nuclear matter, and no known stellar remnant can explain. The stronger the mass estimate and the smaller the emitting region, the more the evidence points toward a horizon at the centers of galaxies. The same logic works on a far greater scale. Stars near the heart of the Milky Way follow tight. Fast orbits around a source that emits little ordinary light. Their paths reveal a hidden mass millions of times greater than the Sun, packed inside a region smaller than the orbit of many familiar solar system bodies. No cluster of ordinary dark objects can remain stable in such a compact space for long. The most natural explanation is a supermassive black hole. The proof is not a picture of the interior. It is the patient mapping of stars moving under the control of an unseen center. Each orbit is a line in the argument. The closer the stars pass, and the faster they swing around the central mass, the tighter the constraints become. The black hole at the galaxy's core is therefore known by choreography. The stars do not explain themselves unless a compact central mass is present, and the mass does not behave like any ordinary object. Around other galaxies, supermassive black holes reveal themselves through even brighter consequences. When gas falls into the central regions of an active galaxy, accretion can release enormous energy. Some galactic cores blaze across cosmic distances, powered not by the black hole shining from within, but by matter outside the horizon losing gravitational energy as it descends. Jets can emerge from the region around the black hole, shaped by rotation and magnetic fields, carrying particles across distances larger than the host galaxy itself. These jets are not streams escaping from inside the event horizon. They are launched from the surrounding environment before matter has crossed the final boundary. The distinction matters because it preserves the central fact. A black hole can power brilliance without emitting light from its hidden interior. It can make a galaxy's core visible because its gravity organizes the motion of matter into one of the most efficient engines in the universe. Then came a different kind of evidence, one that did not rely on light at all. Gravitational waves changed the way black holes could be tested. When two black holes orbit each other, they lose energy through ripples in spacetime. The orbit tightens. The objects move faster. In the final moments, the signal rises in frequency and strength before settling into the quiet pattern of a newly formed black hole. Detectors on Earth measure tiny changes in length as those waves pass through, changes so small that the achievement seems almost unreasonable until the pattern is compared with the predictions of general relativity. The first confirmed detections were not observations of gas, disks, or companion stars. They were direct measurements of spacetime responding to the merger of massive compact objects. The waveform carried the masses of the black holes, the energy released, and the character of the final remnant. For the first time, black holes were not only inferred from what they did to matter. They were heard through what they did to geometry. This matters because gravitational waves test black holes under conditions no telescope can duplicate. The final orbit before merger occurs in the strongest gravity outside the horizons, where spacetime is changing rapidly and general relativity faces one of its sharpest observational trials. The match between predicted and detected waveforms supports the idea that black holes behave very much as the theory says they should. Still, the waves do not open the horizon. They do not reveal the singularity. If such a thing truly exists, they confirm the external dance, the merger, and the final settling of the remnant. The deepest interior remains hidden. Evidence has grown stronger, but the concealment is not removed. Our horizon, by definition, keeps part of the story beyond reach. Even the image of a black hole's shadow follows this rule. When telescopes spread across Earth combine their signals to study the region around a supermassive black hole, they do not photograph the event horizon itself as a solid edge. They image light from hot material bent by gravity around the central darkness. The shadow is the result of photons being captured or redirected near the black hole, producing a dark region surrounded by emission. It is an extraordinary observational achievement, but it is still a portrait of consequence. Light outlines where escape becomes difficult, while the hidden center remains hidden. The pattern agrees with expectations, and that agreement is powerful, yet it also shows the nature of black hole science at its most honest. The object is understood through boundaries, motion, distortions, waves, and surrounding fire. Its reality becomes firmer with each independent line of evidence, even though its defining region cannot send light back. The question that once seemed almost philosophical, whether black holes are real, now has an answer built from many kinds of measurement. Stellar companions point to compact, unseen masses. X-rays show matter heated near extreme gravity. Galactic centers reveal enormous dark objects through stellar orbits. Active galaxies display the energy released by accretion. Gravitational waves record mergers in the fabric of spacetime. Horizon-scale images show the shadow cast by gravity on surrounding light. No single clue carries the entire burden. Together, they form a structure of evidence difficult to replace with anything else. The invisible has become one of the best supported classes of object in astrophysics, not because it has stopped being dark, but because darkness itself has measurable edges. What remains unresolved is no longer whether something massive and compact is there. The harder question is what such an object truly contains when all outward paths end, and whether the physics that describes its exterior can survive the journey toward its hidden center. The edge of a black hole is not where the difficulty ends. It is where the difficulty becomes clean enough to name. Outside the horizon, general relativity works with remarkable authority. It predicts the bending of light, the motion of orbiting matter, the ringing pattern after mergers, and the boundary beyond which no signal returns. The exterior can be tested by telescopes, timing measurements, stellar orbits, and gravitational waves. But the same theory that succeeds so well outside the horizon points inward toward a place where its own language begins to fail. Follow the equations deep enough, and collapse seems to end in a singularity, a region where density and curvature become infinite, and where the ordinary meanings of distance and time lose stability. Physics is usually wary of infinities. They often mark not a real object in nature, but the point where a model has been asked to do more than it can do. In that sense, the singularity is not only a prediction, it is also a warning. It says that the gravitational theory which reveals the black hole may not be sufficient to describe what the black hole finally contains. The horizon can be understood using classical spacetime, smooth and continuous, bent by mass and energy. The center demands something else, because collapse has forced gravity into the same territory where quantum physics can no longer be ignored. Quantum physics governs the small, the uncertain, and the granular behavior of matter and energy. General relativity governs the large, the smooth, and the geometric behavior of spacetime. Most of the universe allows these theories to work in separate domains. A planet orbiting a star does not require a quantum description of spacetime. An electron in an atom does not usually need the full curvature of the cosmos. Black holes bring the two languages into direct contact. Their horizons can be vast, but their deepest interior is compressed towards scales where quantum effects should matter. The problem is not that either theory is weak. It is that both are too successful in their own realms to be casually replaced, yet incomplete when the same event demands them together. A complete theory of quantum gravity would have to explain what spacetime does when it can no longer be treated as a perfectly smooth fabric. It would have to describe whether the singularity is avoided, transformed, or replaced by some deeper structure. At present, no confirmed answer has done this in a way that can be tested as securely as the exterior physics of black holes. Black holes are not merely dense objects. They hide their interiors behind horizons. In ordinary science, a hidden region can often be probed indirectly by what escapes from it. Light leaves a star. Neutrinos escape a supernova. Seismic waves pass through a planet. A black hole denies that ordinary route. After matter crosses the horizon, no message from that matter returns to the outside. The external universe is left with only a few measurable features, such as mass, rotation, and electric charge. This apparent simplicity is sometimes called the no-hair idea, meaning that black holes erase many details of the matter that formed them. A collapsing star, a cloud of gas, or a swarm of particles may carry enormous complexity before falling in. Yet the resulting black hole can appear astonishingly plain from outside. That plainness is elegant, but it also creates unease. Where does all the information go? In physics, information does not simply mean human knowledge. It means the detailed physical state required to describe a system and distinguish it from other possible systems. Quantum theory strongly suggests that information should not be destroyed. Processes may scramble it, hide it, or make it practically impossible to recover. But at the deepest level, the evolution of a system is expected to preserve it. Black holes seem to threaten that expectation. The tension grew stronger when theoretical work showed that black holes should not be completely black. Quantum effects near the horizon imply that they can emit an extremely faint radiation, now known as Hawking radiation, and slowly lose mass over immense timescales. For large astrophysical black holes, this radiation is far too weak to detect directly. But the implication is profound. If a black hole forms from matter carrying information, then radiates away as a nearly featureless thermal glow, what happens to the detailed information about what fell in? If it disappears, quantum theory is wounded. If it survives, it must be encoded in a way that is not obvious in the classical picture of a horizon. This is the black hole information problem, and it has become one of the central puzzles where gravity, quantum theory, and thermodynamics meet. The event horizon, once treated as a one-way boundary in spacetime, becomes a place where the rules of information may be tested in their most extreme form. One clue comes from entropy. A black hole has an entropy proportional not to the volume it encloses, but to the area of its horizon. That fact is strange enough to change how space itself is imagined. In ordinary systems, more volume usually allows more possible internal arrangements. A black hole suggests that the number of hidden possibilities may be tied to its boundary instead. This has inspired the holographic principle, the idea that the information contained in a region of space might be representable on a lower dimensional boundary. It is a careful scientific idea in certain theoretical settings, not a claim that the visible universe is an illusion. Its importance lies in the way black holes force a reversal of expectation. The interior may not be understood by counting ordinary locations inside it. The boundary may carry the deeper accounting. Whether this principle describes the actual universe in a testable way remains unresolved. But it reveals how black holes have turned from astronomical objects into clues about the architecture of physical law. Even the horizon itself has become more complicated. In the classical picture, a large black hole can be crossed without a local observer noticing anything special at the boundary, at least if tidal forces are not immediately destructive. The horizon is globally important, but not necessarily a fiery wall. Yet some attempts to preserve quantum information have suggested sharper possibilities, including proposals in which the horizon is not as smooth as relativity implies. Other ideas argue that information is subtly encoded in radiation, or in correlations that only become meaningful across the full lifetime of the black hole. The debate is not settled by dramatic images, because the relevant effects are too faint, too hidden, or too far beyond current experiments. The black hole becomes a thought laboratory made real by astrophysical evidence. It exists in the sky, merges across cosmic distances, bends light, and powers accretion disks. Yet its deepest lesson may depend on processes no telescope can directly resolve. This is the unusual position of black hole physics, grounded by observation at the exterior, speculative at the interior, and forced to remain honest about the line between the two. Singularities also raise a question about time. Inside the horizon of a non-rotating black hole, the direction toward the center behaves less like a place one may choose to approach and more like a future that cannot be avoided. The geometry turns inward motion into destiny. In rotating black holes, the mathematics becomes richer and more troubling, with inner horizons and possible extensions that hint at paths through the equations but may be unstable in any realistic collapse. These solutions are valuable because they reveal what the mathematics permits under idealized conditions. But nature may not preserve their delicate structures. Real black holes form from messy matter, magnetic fields, radiation, and perturbations. The universe rarely respects perfect symmetry. The tension between elegant solutions and physical reality is part of the edge. A mathematical doorway may not be a cosmic passage. A possible extension of spacetime may not survive the slightest disturbance. Some approaches to quantum gravity replace the singularity with a bounce, a dense quantum region, or a transition into another spacetime. Others suggest that the interior is encoded in subtle boundary degrees of freedom, or that spacetime itself emerges from quantum entanglement. These are not interchangeable answers, and none has become the confirmed ending of collapse. They are attempts to follow the evidence past the point where classical relativity stops being complete. Their value is not in giving the black hole a more exotic story. Their value is in showing how sharply the object exposes the unfinished foundation beneath modern physics. A black hole is therefore both a real astronomical body and a controlled failure of understanding. Its exterior confirms a theory of gravity with extraordinary precision, while its interior asks for a theory that has not yet been secured. This is why the question of what black holes truly are has not ended with their detection. Observation has moved them from speculation into the catalog of real cosmic objects. It has not dissolved the deeper problem. At the horizon, the universe draws a boundary around missing information. At the center, the equations point toward a place where smooth spacetime may lose its meaning. Between those two limits lies the reason black holes remain more than collapsed stars. They are places where known science is strongest at the edge and most uncertain at the core, leaving physics with a dark object that can be measured, mapped, and trusted, while still refusing to reveal the final rule by which gravity and the quantum world become one. Oumuamua entered the solar system without belonging to it. Its path gave away the fact before its surface could tell any story. Most comets and asteroids that circle the sun follow orbits shaped by the sun's long control, stretched or tilted perhaps, but still bound to the solar system by gravity. Oumuamua did something different. It arrived on a hyperbolic trajectory, moving too fast and at too sharp an angle to have been merely disturbed from the outer edge of the sun's own family. It was not a returning comet from the distant Oort cloud. It was a traveler from interstellar space, passing once through the inner solar system and then leaving again, never to come back. The object was small, faint, and retreating when astronomers recognized what it was. So the evidence came in fragments. Its brightness changed as it rotated, suggesting an elongated or flattened shape, though the exact form remains uncertain. Its color appeared reddish, like many small bodies in the cold outskirts of the solar system. It showed no obvious coma. The glowing cloud of gas and dust that normally surrounds an active comet near the sun. Yet its motion contained a slight extra acceleration that gravity alone did not fully explain. Each clue was modest. Together they made the object more difficult to place into any familiar category. Oumuamua became important not because it answered a question, but because it proved that the solar system is not closed. Material from other stars can cross the planetary region, carry records from unknown environments, and vanish again before its meaning is secure. The red surface is one of the quieter clues. In the outer solar system, many icy bodies develop dark red coatings after long exposure to radiation. Cosmic rays and ultraviolet light alter simple carbon-rich molecules, slowly building complex organic residues known as tholins. These are not life. They are not even evidence that life exists nearby. But they are chemically interesting because they show how space can process simple ingredients into larger organic compounds across long spans of time. If Oumuamua carried such a surface, then it may have spent ages outside the shielding influence of any star, exposed to energetic particles in the thin medium between stellar systems. Interstellar space is not empty in the absolute sense. It contains gas, dust, magnetic fields, radiation, and cosmic rays moving through the galaxy. A small object drifting there can be altered atom by atom. Its outer layers can become a radiation crust, a record of exposure written not in words but in chemistry, color, and texture. The surface of Oumuamua may therefore have been less like a fresh fragment and more like weathered material from a long crossing through the galactic environment. That does not reveal where it was born, but it changes the scale of the object. It is not merely a rock or an icy remnant. It is a surface that may have carried the effects of another star system and the space between stars. Its origin remains uncertain. It may have been thrown out during the formation of planets around another star, when gravitational encounters scattered debris into interstellar space. Young planetary systems can be chaotic places. Giant planets migrate. Smaller bodies collide. Icy planetesimals are flung inward or outward. Some remain bound, becoming comets, asteroids, or distant reservoirs. Others are ejected entirely and begin wandering between stars. If this is common, the galaxy may be filled with small exiles from planetary birth, each one a leftover from the building of worlds. Oumuamua would then be the first recognized member of a vast population, not an isolated accident. It crossed the solar system only because its path happened to intersect the narrow region where human instruments were watching. The thought is humbling. The object itself was tiny compared with planets and stars, but its detection implies a galaxy littered with fragments of formation, carrying materials from places that may never be observed directly. Every stellar system may lose part of itself to the dark, and some of that lost matter may eventually pass through the domain of another star. The puzzling acceleration sharpened the debate. Comets often accelerate slightly when sunlight warms their ice, and escaping gas acts like a weak thruster. Oumuamua, however, did not show the visible dust and gas expected from ordinary cometary activity. This absence forced several possibilities into view. Perhaps it released gas without much dust, making the outflow difficult to see. Perhaps it carried unusual volatile materials that escaped in subtle ways. Perhaps its shape and rotation affected how sunlight pushed on it. Though that explanation requires careful limits, more speculative ideas appeared as well. But the strongest scientific approach begins with ordinary physics and only moves outward when ordinary explanations fail. The data were too limited to settle the matter. Oumuamua was already dimming, and no mission could reach it. The object became a reminder of how brief some discoveries are. A visitor can be recognized only after it is leaving, and the time for close study can close almost as soon as the question opens. That is part of what made the encounter so valuable. It revealed not just a body, but a weakness in readiness. The solar system had received an interstellar sample, and science had only enough time to take a distant, partial reading. A later visitor, Comet Borisov, showed a different face of the same larger phenomenon. Unlike Oumuamua, Borisov behaved more like a familiar comet, producing a visible coma and releasing gas as it approached the sun. Its interstellar orbit marked it as foreign, but its activity made it easier to interpret. It suggested that at least some objects from other systems resemble the icy bodies already known around the sun. This comparison matters because one strange object alone can mislead. Two visitors, different in behavior, begin to show range. Interstellar debris is not one type of thing. It may include icy comets, rocky fragments, radiation-hardened shards, and bodies altered by collisions or by long exposure to galactic space. Each new detection has the potential to separate what is common from what is exceptional. Oumuamua remains unusual, but unusual does not mean impossible. It may be telling science that the categories built from local examples are too narrow. The solar system's small bodies are not a complete guide to what other systems produce and eject. Interstellar messengers also deepen the question of organic chemistry. Organic molecules are widespread in space. They appear in molecular clouds, meteorites, cometary material, and the surfaces of distant icy worlds. Their presence does not prove biology, but it shows that carbon chemistry is not rare or fragile on cosmic scales. If objects ejected from young planetary systems carry organics, then they can move those compounds between stars. This does not mean life itself travels easily, and it does not require any dramatic claim about seeded planets. It simply widens the geography of chemistry. The ingredients from which life may someday arise are not confined to one planetary nursery. They can be made, altered, frozen, irradiated, and transported across immense distances. A fragment passing through the solar system may carry a small sample of that wider chemical circulation. It may have formed in a disk around a star that is now far away, in a region where planets were still assembling, then spent millions or billions of years in darkness before briefly reflecting sunlight near Earth's orbit. By the time it is noticed, it is already leaving, and its surface has become the only accessible witness. The scientific response has changed since Oumuamua. Surveys are improving, and future observatories may find interstellar objects earlier, while they are still approaching rather than fading into escape. Earlier detection could allow more detailed spectroscopy, better tracking of acceleration, and perhaps someday a spacecraft mission designed to intercept such a visitor. The difficulty is speed. Interstellar objects move quickly relative to the Sun, and their paths are not known in advance. A mission would require readiness before the target is discovered, or a spacecraft already positioned to respond. The next messenger may not wait. It may enter from an unexpected direction, brighten briefly, expose a small part of its chemistry, and depart into the dark before plans can catch up. Yet even distant observation would be worthwhile, because each object adds a point to a map that is currently almost blank. Oumuamua's importance lies in that opening. It made the solar system porous in a new observational sense. The boundary between the Sun's domain and the rest of the galaxy is not a wall, but a region crossed by particles, fields, radiation, and occasionally solid matter from elsewhere. The same space that carries cosmic rays and gas can also carry fragments of planetary systems. Small bodies with surfaces modified by long exposure and interiors, perhaps preserving older materials. These objects are not grand in size, but they are grand in implication. They suggest that formation, loss, wandering, and encounter are part of the ordinary life of the galaxy. A planetesimal can be born near one star, exiled by gravity, darkened by cosmic rays, and briefly illuminated by another star before returning to interstellar night. In that passage, the object becomes a messenger without intention and without return, holding a thin record of places that may never be reached. The mystery is not only what Oumuamua was. It is how many such fragments are moving unseen between the stars, and what quiet histories are passing through the solar system before observation has learned to meet them in time. Cosmic weather begins where the Sun's comfort starts to lose its authority. Beyond the planets, beyond the familiar orbits and the scattered icy bodies at the solar system's edge, the Sun is still active, still sending out a stream of charged particles called the solar wind. This wind carries a magnetic field outward, shaping a vast protective bubble known as the heliosphere. Inside that bubble, Earth and the other planets move through a region partly shielded from the harsher environment between the stars. Outside it, interstellar space is not empty silence. It is crossed by particles moving at near light speed, threaded by magnetic fields, stirred by ancient explosions, and filled with thin gas that remembers the deaths of stars. The word weather is useful only if it is enlarged far beyond clouds and rain. In this setting, weather means streams of charged matter, radiation, magnetic turbulence, and energetic particles that can travel across the galaxy. The solar system is not drifting through a void that leaves it untouched. It is moving through an active medium, and the boundary between the sun's domain and the galaxy is a living frontier, pressed from both sides. The most penetrating agents of this environment are cosmic rays. Despite the name, they are not rays in the ordinary sense, but fast particles, often protons or atomic nuclei, carrying enormous energy. Some are born in solar storms, but the most powerful come from beyond the solar system. A supernova can help create them. When a massive star explodes, the shock wave plows into surrounding gas, compressing and tangling magnetic fields. Charged particles caught in that moving field can be accelerated again and again, gaining energy until they escape into interstellar space. Other extreme environments may contribute as well, including regions near black holes, neutron stars, and powerful stellar winds. By the time these particles cross the galaxy, their paths have often been twisted by magnetic fields, so tracing a single cosmic ray back to its source is difficult. It may arrive at Earth from one direction while its true origin lies elsewhere. The particle itself carries energy, not a simple address. This makes cosmic rays both evidence and mystery. They reveal that the galaxy contains natural accelerators of immense power, but their tangled journeys hide the full geography of those engines. When cosmic rays enter matter, they do not behave gently. A high-energy particle can strike atoms in an atmosphere, breaking them apart and creating cascades of secondary particles. Most of this shower is absorbed before it reaches the ground, which is one reason Earth's atmosphere is more than a layer of air. It is a shield. The planet's magnetic field adds another defense by redirecting many charged particles before they can enter deeply. Together, the magnetosphere and atmosphere turn a dangerous cosmic environment into one that life can endure at the surface. Without them, radiation would be harsher, chemical stability more difficult, and biological systems more exposed. This protection is not perfect, and it does not need to be. A small fraction of energetic particles still penetrates, and their effects can be subtle. Radiation can damage genetic molecules. It can alter atoms, break chemical bonds, and create mutations. Most such damage is harmful or neutral, but mutation is also part of the long machinery of evolution. Life is shaped by inheritance, variation, and selection, and some variation arises because the environment is never completely sealed away from the wider cosmos. In that restrained sense, interstellar space reaches into biology. It does not guide life with intention, but it helps provide one source of change on which natural selection can act. The same particles that threaten living tissue also belong to the background conditions under which life has evolved. This double character is common in planetary science. Too much radiation can sterilize or damage. Too little change may narrow the possibilities for adaptation. Earth exists between exposure and shelter. Its surface is protected enough for oceans, cells, forests, and complex animals, but not so isolated that the galaxy has no influence at all. The heliosphere adds another layer to this balance. It is not a hard wall. It is a region where the solar wind slows, presses against interstellar material, and forms a boundary whose shape changes with solar activity and the surrounding medium. The sun moves through the Milky Way, and the heliosphere moves with it, more like a bubble being carried through a thin galactic sea than a fixed sphere. Its size and form can shift as the solar wind strengthens or weakens, and as the solar system passes through regions of different interstellar density. If the surrounding medium becomes denser, the heliosphere may be compressed. If solar activity changes over long periods, the shielding may vary. This means the radiation environment of Earth is not controlled only by the planet. It also depends on the behavior of the Sun and the solar system's larger galactic surroundings. The quiet blue sky is therefore linked to boundaries far beyond Neptune. A change at the edge of the heliosphere can alter the number of galactic cosmic rays entering the planetary region. The effect at Earth's surface may be moderated by atmosphere and magnetism, but the connection remains. The planet lives inside nested shields, and each shield belongs to a different scale. The atmosphere belongs to Earth. The magnetosphere belongs to the planet's core and its magnetic field. The heliosphere belongs to the Sun. Beyond that lies the galaxy, with its supernova remnants, magnetic fields, and charged particles. None of these layers is absolute. Each reduces, redirects, or filters what comes from outside. Life persists not because the universe is gentle, but because Earth is placed inside a series of partial protections that together make gentleness possible. Interstellar space can also disturb the solar system in slower, more gravitational ways, far beyond the known planets. The Sun is thought to hold a vast reservoir of icy bodies in the distant Oort cloud. These objects are weakly bound, so far from the Sun that a passing star or the tide of the galaxy can shift their orbits. Some can be nudged inward, becoming long-period comets that fall toward the planetary region. This is another form of cosmic weather. Not radiation, but gravitational disturbance. Nearby stars do not need to collide with the solar system to matter. Their gravity can stir its outskirts, changing the paths of bodies that were otherwise almost still. Most incoming comets will pass harmlessly. Some may become beautiful temporary visitors. A rare few could become dangerous if their paths cross a planet. The galaxy touches Earth not only through particles, but through the architecture of orbits. This connection softens the old image of the solar system as isolated. The Sun protects, but it also moves. Its planets are sheltered, but not detached. The Milky Way is not a distant backdrop against which the solar system happens to sit. It is the environment through which the solar system travels. Stars pass at great distances. Molecular clouds drift. Supernova enrich and disturb the interstellar medium. And magnetic fields guide particles across scales that dwarf planetary space. For life elsewhere, these shields and exposures may be decisive. A planet around a calm star with a strong magnetic field and thick atmosphere may hold its surface environment for long spans. A planet around an active red dwarf may face frequent flares, intense radiation, and atmospheric stripping unless it has enough protection. A world with no magnetic field might still survive if its atmosphere is massive or its star is mild. But the margin changes. Habitability is not only about distance from a star or the presence of liquid water, it is also about weather from space, about whether an atmosphere can last, whether surface chemistry can remain stable, and whether radiation is filtered without sealing the world from all cosmic influence. The search for life must therefore include the invisible conditions surrounding a planet. The sky above a living world is not merely an opening to starlight. It is a shield, a boundary, and a record of its star's temperament. The solar system's own weather reveals this with quiet force. Auroras shimmer when charged particles are guided by Earth's magnetic field into the upper atmosphere. Solar storms can disturb satellites, power systems, and radio communication. Cosmic rays create faint showers high above and sometimes reach deep enough to leave traces in detectors and living tissue. Farther out, the heliosphere bends under galactic pressure. And farther still, Icy bodies wait for gravitational nudges from passing stars. These events operate on different timescales, from minutes to millions of years. Yet they belong to one continuous setting. Earth is not simply beneath the universe. It is inside it, protected by local conditions while remaining connected to distant violence, ancienne explosion, and the restless medium between stars. The storm outside the bubble is not always fierce, and it is not always hostile. It is the normal weather of a galaxy, filtered by the sun, softened by the planet, and still present in the background of every living system. What makes it mysterious is not only its danger, but its intimacy. The same cosmic environment that can threaten atmospheres, alter genetic molecules, and disturb distant comets also supplies the energetic and chemical setting in which planets become part of galactic history. The search for habitable worlds begins with a simple phrase that becomes less simple the longer it is followed. Follow the water sounds clear because every living cell on Earth depends on liquid water, and because water is a remarkable solvent, able to carry dissolved minerals, support complex chemistry, and remain stable across a useful range of temperatures and pressures. Around other stars, that principle gives astronomy a first guide. A rocky planet too close to its star may lose its oceans to heat. A planet too far away may lock its water into ice. Between those extremes lies the habitable zone, the region where liquid water could exist on a surface if the atmosphere cooperates. Yet the phrase hides many conditions inside the word could. A planet can sit in the right orbital region and still be sterile, unstable, stripped of air, buried beneath ice, or wrapped in an atmosphere too thick for familiar chemistry. Water is necessary for life as it is known, but necessity is not the same as sufficiency. The search does not end when water appears. It becomes more careful. The first discoveries of planets beyond the solar system changed the scale of the question. At first, many were unlike anything familiar. Giant worlds orbiting close to their stars, massive planets in places where the solar system had not prepared astronomers to expect them. Detection methods favored such objects because large planets tug their stars more strongly or block more starlight when they pass in front. As instruments improved, smaller worlds appeared in the data. Super-Earths, mini-Neptunes, compact planetary systems, and worlds around red dwarf stars began filling the catalog. The galaxy did not seem to produce planetary systems as copies of the Sun's family. It produced diversity. Some planets are scorched. Some are frozen. Some may be mostly rock. Some are wrapped in deep envelopes of gas. Some orbit stars so cool and dim that their habitable zones lie close in, where tidal forces may lock one side of the planet toward permanent day and the other toward permanent night. The search for another Earth therefore became less like finding a duplicate and more like learning the range of environments in which habitability might survive. Among the most intriguing and difficult cases are water-rich worlds. Earth is called a blue planet, but by mass it contains only a small fraction of water. Its oceans are thin compared with the size of the planet. Resting on a rocky surface where continents rise, seafloors spread, minerals dissolve, and carbon cycles through air, sea, rock, and life. This mixture matters. The shoreline is not only a boundary in scenery, it is a chemical meeting place. Weathering brings minerals from land into water. Hydrothermal vents supply heat and dissolved compounds from below. Plate tectonics helps recycle carbon and regulate climate over long spans. Though whether plate tectonics is strictly required for life remains uncertain. Earth's habitability depends not simply on having water, but on having water in contact with rock, under an atmosphere, with energy sources and cycles that can keep chemistry moving. A planet with far more water may lose some of these advantages. Too much of a necessary thing can become a barrier. A deep ocean world may contain hundreds or thousands of kilometers of water above its rocky interior. Under such pressure, water can form exotic high-pressure ice, not because the environment is cold in the ordinary surface sense, but because pressure changes the structure water molecules can take. This ice would not float like familiar ice on a winter lake. It could form a dense layer at the base of the ocean, separating liquid water above from rock below. If that happens, the ocean is no longer directly fed by minerals from the crust. Hydrothermal chemistry may be cut off. Nutrients may become limited. Energy pathways may narrow. The world may possess an ocean larger than anything on Earth and still lack the active water-rock exchange that made Earth's oceans chemically alive. The image is counterintuitive. A planet covered in water might seem more inviting than a dry one. But if its ocean is too deep, its seabed may be sealed away behind a pressure-made wall of ice. In that case, habitability turns not on abundance, but on proportion. Water must be present, but it must also be placed where it can interact. The planet known as GJ1214b became a symbol of this difficulty because it appears to belong to a class of worlds larger than Earth but smaller than Neptune. Such sub-Neptunes are common in exoplanet surveys. Even though the solar system has no exact example, some may have thick, hydrogen-rich atmospheres. Some may contain large amounts of water or volatile material. For a time, a water world seemed like a hopeful phrase. But hope changes when the details sharpen. A dense steam atmosphere, enormous pressure, and a deep global ocean can create conditions very different from Earth's seas. The question is not whether water exists somewhere in the planet. The question is whether it exists in a form that can support sustained chemical complexity. If a thick atmosphere traps too much heat, the surface may become a high-pressure, high-temperature environment hostile to familiar biology. If the ocean is too deep, nutrients from rock may be isolated. If there is no land, the cycles that concentrate and redistribute key elements may be weakened. The planet can be wet and still not be welcoming. This does not make such worlds unimportant. They are crucial because they teach the search to move beyond slogans. Habitability is a system, not a single ingredient. The same lesson applies to planets around red dwarfs, the most common stars in the galaxy. Their abundance makes them attractive targets, and their small size makes transiting planets easier to detect. A planet in a red dwarf's habitable zone may pass frequently across the star's face, offering repeated chances to study its atmosphere. But red dwarfs can be active, especially in youth, producing flares and radiation that may erode atmospheres or alter surface chemistry. A planet close enough to receive Earth-like warmth may also become tidally locked, with one hemisphere receiving constant starlight and the other remaining dark. This does not automatically make life impossible. Atmospheres and oceans can move heat. A twilight band between day and night might hold stable conditions. Clouds can reflect light and moderate climate. But the situation is delicate. The same closeness that makes warmth possible can bring hazards. A habitable zone around such a star is not simply a ring of comfort. It is a region where atmospheric survival, magnetic shielding, stellar behavior, and climate circulation must all work together. The search for life, therefore, becomes a search for balance across many layers. Temperature matters, but so does pressure. Water matters, but so does chemistry. Atmosphere matters, but so does whether it can last. A planet's mass can help it hold air. Yet too much mass may create crushing pressure or a thick gaseous envelope. A star's light can power climate and photosynthesis. Yet too much ultraviolet radiation can damage molecules and strip atmospheres. Volcanism can refresh gases and nutrients. Yet excessive activity can destabilize climate. Plate tectonics may help regulate carbon dioxide. Yet worlds without plate tectonics might still maintain some other long-term balance. No single measure carries the full meaning of habitability. This is why Earth remains both guide and warning. It is the only known living world, so its conditions cannot be ignored. But treating Earth as the only possible pattern may make the search too narrow. Life elsewhere might use familiar chemistry in unfamiliar settings. Perhaps beneath ice, within subsurface oceans, or under atmospheres that differ from Earth's, while still permitting liquid water somewhere stable. The difficulty is recognizing possibility without turning every possible world into a promise. Observation is improving. When an exoplanet crosses in front of its star, a small fraction of starlight may pass through the planet's atmosphere. Molecules absorb particular wavelengths, leaving faint signatures that telescopes can search for. Water vapor, carbon dioxide, methane, and other gases become clues, though difficult ones. Clouds, ASAs, stellar activity, and instrumental limits can confuse interpretation. A gas can be produced by life, but also by non-living processes. Oxygen may be suggestive in one context and misleading in another. Methane paired with other gases may be interesting, but only if the planet's environment is understood well enough to rule out simpler explanations. The future of the search depends on combining signals, not trusting one sign too quickly. A living world is not likely to announce itself with a single unmistakable word. It may appear first as a pattern of atmospheric imbalance, surface condition, stellar setting, and planetary history that resists ordinary explanation. Wandering through the catalog of exoplanets, the most important realization may be how narrow and how generous the universe appears at once. Narrow, because Earth-like stability requires many things to go right across long spans. Generous, because planets are abundant. Chemistry is widespread, and nature has built more kinds of worlds than one solar system could have suggested. Water worlds, desert planets, tidally locked planets, ocean moons, super-Earths, and sub-Neptunes all widen the field of imagination while tightening the standards of evidence. The goal is not to find a world that merely resembles Earth from a distance, but to understand which combinations of rock, water, air, light, and time can keep chemistry open long enough for life to become more than a possibility. The difficult Earth-like place may not be a twin. It may be a planet or moon where balance has taken another shape, where water is neither absent nor overwhelming, where energy flows without destroying, and where the boundary between geology and chemistry remains alive. Until such a world is found, habitability remains a measured hope, held between abundance and constraint. Guided by the blue planet that is known and by the many strange worlds that show how much the word habitable still has to learn, open horizons do not appear only at the far edge of knowledge. They appear wherever the evidence becomes strong enough to reveal the next uncertainty with sharper outlines. The universe's greatest mysteries are not vague gaps left by ignorance alone. They are shaped by what has already been learned. The cosmic microwave background turns the beginning from a mythic darkness into a measurable afterglow. But it does not disclose why the early universe existed in the first place, or why its conditions were so finely suited to later structure. Inflation offers a way to understand the strange smoothness of the ancient sky and the tiny fluctuations that became galaxies. But its own engine remains partly hidden behind energies no instrument can directly recreate. Spacetime explains gravity with extraordinary elegance, bending light, slowing clocks, carrying waves, and expanding across cosmic history. Yet, it may not be the final layer of reality. Time flows with an arrow tied to entropy and the special order of the early cosmos. But the reason that beginning was so special remains one of the quietest and deepest problems in physics. Each answer opens a more precise question. Each discovery narrows confusion without closing wonder. This is the pattern that gives modern cosmology its unusual calm. It does not need the universe to be unknowable in order to feel vast. It becomes vast because some parts are known with care. And those known parts lead to boundaries that are real. The Big Bang is supported by expansion, ancienne radiation, and the abundance of light elements. But the first instant itself remains beyond secure description. Black holes are supported by stellar orbits, X-rays, gravitational waves, and horizon-scale images. But the interior beyond the event horizon is still hidden from ordinary evidence. Interstellar objects have been seen passing through the solar system, but their home systems, full histories, and internal compositions remain largely inaccessible. Exoplanets crowd the galaxy, but a confirmed living world beyond Earth has not yet been found. The universe has become less empty and less simple with every improvement in observation. At the same time, it has become more disciplined. Speculation has to pass through measurement. Mystery has to stay close to evidence. The result is not a smaller cosmos, but a clearer one, filled with questions that have earned their place. The first great mystery concerns origin, not simply whether the universe was once hotter and denser, because the evidence for that is strong. But what kind of explanation can reach beneath the earliest describable state? If time itself is part of the universe, then asking what happened before the beginning may not be straightforward. Before may be a word that belongs inside time, not outside it. Yet physics continues to search for deeper descriptions, because the known equations appear incomplete at the highest densities and smallest scales. Some ideas imagine a bounce from an earlier contracting phase. Others explore quantum creation, multiverse scenarios, or the emergence of spacetime from a more basic structure. None has become a settled account. The difficulty is not a lack of imagination. It is the narrowness of evidence. A successful theory would need to do more than sound profound. It would need to connect with observable traces, perhaps in the pattern of ancient radiation, the distribution of galaxies, or subtle signs from primordial gravitational waves. Until then, the beginning remains a frontier where caution is not weakness, but precision. Science can say that the universe was once hot, dense, expanding, and filled with radiation. It cannot yet say why there was a universe with those properties at all. The second mystery concerns the nature of the stage itself. Space-time behaves like geometry, but also like something physical enough to ripple, stretch, and respond. It carries gravitational waves across cosmic distances. It changes the rate of clocks. It curves around mass and energy. In cosmology, it expands. In black holes, it forms horizons. But whether spacetime is fundamental remains uncertain. If quantum gravity is needed, then space and time may not be smooth all the way down. They may emerge from relationships not yet visible in ordinary experience. perhaps from quantum information, entanglement, or some deeper mathematical structure. This possibility is not science fiction when treated carefully. It arises because the current theories, both powerful and incomplete, meet at places where neither can stand alone. The early universe and black hole interiors are the two most persistent reminders. They are not random curiosities. They are pressure points in the foundation of physics. A horizon can be measured from outside, yet it hides the region where the most important reconciliation may be needed. The cosmos can be traced back to a hot, dense state, yet that state asks for a description of gravity under quantum conditions. The largest scales and the smallest scales fold toward the same missing theory. The third mystery concerns time. The universe does not merely exist. It unfolds. Events leave traces. Stars age. Planets cool. Biology evolves. The past becomes recorded while the future remains open in a practical sense. Even if some views of spacetime treat all moments as part of a larger structure, entropy gives the arrow a physical basis. But it also points backward to the early universe. Why did the cosmos begin in a low entropy condition from which complexity could grow? Why was there room for stars, galaxies, chemistry, and memory? The eventual future may be one of fading gradients, a long approach toward a universe where useful differences become scarce. If so, the age of stars is not the permanent state of reality, but a luminous interval, a time when matter is gathered enough, energy flows strongly enough, and chemistry is active enough for complexity to flourish. That thought does not need to be sorrowful. It gives the present cosmic era a certain delicacy. The universe is not static background. It is a phase in an immense thermodynamic story. Life, thought, and observation belong to a middle time, after the first fire and before the final quiet becomes complete. The fourth mystery concerns darkness. Not only the darkness of black holes, but the deeper, unseen contents of the universe. Galaxies rotate and clusters bend light in ways that point toward dark matter, a form of mass that interacts gravitationally but does not shine like stars or gas. Cosmic expansion appears to be accelerating, a behavior often attributed to dark energy, though its true nature remains unknown. These subjects have moved beyond the outline of the current journey, but they belong naturally to its open horizon. They show that even the visible grandeur of the cosmos may be a minority component. Stars, nebulae, planets, and ordinary atoms may be the familiar surface of a deeper inventory. The universe is not only difficult because it is large. It is difficult because most of its influence may come from forms not directly seen. Gravity reveals what light conceals. Expansion reveals what matter alone cannot explain. The more precisely the universe is measured, the more clearly it points toward hidden ingredients. The fifth mystery concerns life. Earth proves that the universe can make at least one world where chemistry becomes biology, where matter records information, adapts, and eventually studies the sky that made it possible. Exoplanet science has shown that planets are common, and chemistry has shown that organic molecules are widespread. Interstellar objects, comets, meteorites, and molecular clouds all suggest that carbon-based ingredients travel through space in many forms. Yet no second biosphere has been confirmed. The silence is not proof of absence. It is a measure of how hard the search remains. A living planet may need water, rock, energy, atmosphere, stability, and time in the right proportions. Too little water can end possibility. Too much can seal the ocean away from the minerals it needs. Too much radiation can destroy fragile molecules. Too much shielding might limit useful chemistry. Life may be common in hidden microbial forms or rare because long-term habitability is difficult. Intelligence may be rarer still, or it may not advertise itself in ways easily recognized. The question of life beyond Earth is therefore not a single question. It is a chain of uncertainties, from planetary formation to atmospheric survival, from chemistry to biology, from simple cells to detectable worlds. Across all of these mysteries, one theme remains steady. The universe is readable, but not transparent. It leaves radiation from its youth, waves from its collisions, shadows around its black holes, chemical traces on wandering bodies, and faint signatures in exoplanet atmospheres. It gives evidence, but it gives it indirectly, through distortions, remnants, probabilities, and patterns. This is why the journey through cosmic mysteries becomes calm rather than chaotic. The unknown is not a blank wall. It is a landscape with marked paths ending at misted edges. Behind each edge may be a deeper law, a missing observation, or a correction to an old assumption. The task of science is not to remove mystery by force, but to give it form. The greatest questions endure because they sit at the meeting point between what can be measured and what is still beyond reach. Origins, spacetime, time's arrow, black holes, interstellar messengers, cosmic weather, and habitable worlds are not separate wonders scattered at random. They are connected expressions of a universe that changes, records, hides, and reveals. The open horizon is therefore not an ending. It is the present condition of knowledge, wide enough to remain unfinished and firm enough to keep guiding the next careful look into the dark. The journey settles not because the questions are finished, but because their shapes have become clearer. The universe holds its oldest light in a cold background glow, carries the marks of expansion in the stretching of space, bends time and distance around matter, and hides some of its strongest secrets behind horizons that no signal can cross. Its mysteries are not distant decorations. They are woven into the same reality that allows stars to form, planets to cool, oceans to gather, and chemistry to become alive in at least one known place. Every answer reached along the way has carried a quiet boundary with it. The early universe can be traced, but not yet fully explained. Black holes can be measured, but not opened. Interstellar visitors can be recognized, but often only as they leave. Exoplanets can be counted by the thousands, but life beyond Earth remains unconfirmed, patient, and unresolved. That is the calm discipline of cosmic knowledge. It does not turn wonder into certainty too quickly. It allows evidence to speak in faint radiation, altered light, drifting particles, careful orbits, and the slow behavior of worlds. The darkness beyond the stars is not empty of meaning. It is filled with old signals, hidden structures, unfinished physics, and possible places where matter may have found other ways to organize itself. For now, the universe remains open, not as a riddle demanding haste, but as a vast record still being read. Its greatest mysteries continue outward, across spacetime, through ancient light, around silent black holes, between wandering worlds, and into the long future where new observations may give the unknown firmer edges. In that quiet openness, the cosmos does not feel smaller for being studied. It becomes more spacious, more patient, and more deeply connected than it first appeared.